All right, week 30, part 2, partial sums and sigma notation. So, sometimes we're interested in adding the terms of a sequence. So, here we have some sequence of numbers, 1/2, 1/4, 1/8, 1/16. Looks like the pattern is, well, the denominator doubles. We multiply by 1/2 each time. So, we can say, we call this S sub 1, and we can say this is the first partial sum, and it's just the sum of, well, the first term. Second partial sum, S sub 2, is the sum of the first two terms. Third, sum of the first three terms, etc. And we call them partial sums because sometimes, sometimes we're going to be adding, we can actually add an infinite number of terms and come up with some finite value, which is pretty cool. And if you remember, ask me to tell you the Snickers bar story. So let's take a look at our values here, and we get something like this. So first partial sum, 1/2, well, that's just 1/2. 1/2 plus 1/4 is 3/4. Do your common denominator stuff. 1/2 plus 1/4 plus 1/8 is 7/8. And for the fourth partial sum, we end up with 15/16. So we're looking for some pattern, right? Our first is 1/2. Our second is 3/4, our third is 7/8, and our fourth is 15/16. Okay, yeah, there's a couple typos in here, but we'll catch them, don't you worry. So, you might recognize that this is, yes. Might recognize that 2 to the first is 2, and 2 to the second, for the second partial sum, is 4. 2 to the third partial sum, 8, and 2 to the fourth partial sum is 16. Look at that, cut that typo. All right, so our pattern is we're seeing 2 to the whatever, 2 to the n down here, and the top number, the numerator, is 1 less than the denominator. So if we were actually writing that out, because this is what we'll be doing, the crux of the issue, the great fun challenge is find the nth partial sum. Meaning if your teacher said, hey, add up, the first 1,000 terms, right? You could sit there for a couple hours with the calculator, or you could say, you know what? I think that's going to be, what am I drawing? 2 to the 1,000 minus 1 over 2 to the 1,000. Which, by the way, is going to be really close to 1, but that's what it would be if you added up the first 1,000 terms. I like that as a test question or something, ha ha ha. But there'd be an easy way to solve it. So this is how we would write that, S sub n, indicating nth partial sum, and we have 2 to the n minus 1 over 2 to the n. Okay, so this is what we are practicing with, partial sums. Second example says, find the first 4 partial sums and the nth partial sum. And here, instead of being given the terms of the sequence, we're given an explicit formula. So, from this, what we would do is first plug in 1 to find the first term, and then 2 to find the second term, 3 to find the third term, and 4 to find the fourth term. So that's what we have over here. And I started doing that, and I was recognizing, so we got, I plugged in 1, I plugged in 2, and then it was like, oh look, this is 1 minus 1/2, this is 1/2 minus 1/3, this is 1/3 minus 1/4, and this is 1/4 minus 1/5. So this pattern in the numbers, before we even calculate, right, that is, well, that's 1/2, and 1/2 minus 1/3 would be 1/6, etc. What would this be, 1/12? Before we calculate those, if we look at what we're doing, we're finding these partial sums. So let's start adding them up. I'm trying to hide that bottom answer there. So we start adding them up where the first partial sum is 1 minus 1/2, which is 1/2. And the second partial sum, meaning this plus this, so we have our first term plus our second term, but do you see how if we write it like this, we got this minus plus, and the 1/2s go away, and that simplifies it a little bit. Third partial sum, we got the first term plus the second term plus the third term, and the 1/2s cancel out, the 1/3s cancel out, and we have 1 minus 1/4. And similarly for the fourth partial sum, first, second, third, and fourth terms all added together. Cancel, 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 cancel. We like that. All right, 1 minus 1/5. So what we're looking at is this for our first partial sum, second, third, and fourth partial sum. So is there some relation between one, our first and this, our second and this, third and this, fourth and this? So hopefully you're recognizing, hey, for our first we have a 1 up above, and then this is 1 greater. For our second we have a 2 up above, and this is 1 greater. Third we have 3 up above, this is 1 greater. Fourth we have 4 up above, this is 1 greater. I wish I could talk faster. So if we, aha, caught you. If we write it this way as, so S sub n, meaning the nth partial sum, is going to be n over n plus 1. And that totally agrees with all of this. So we'd have 1 over 1 plus 1, 2 over 2 plus 1, 3 over 3 plus 1, 4 over 4 plus 1 as the sum of all those terms added together. So your teacher says, hey, what's the sum of the first 1,000 terms? Instead of sitting there for hours, you could say 1,000 over 1,001. All right, and there are applications of this in everyday life, finance and whatnot. Okay, let's take a look at page 2. Where are we going? I'm going to pause for some humor here. Look, a joke. Get it? Ah! All right, sigma notation. So this is the Greek letter sigma, and it basically means add. Add them up. All right. So this is how this is said, and this is how we do this. We have something that looks like this. We got sigma, we have k equals 1, and some function here, a sub k, and it's going to equal the sum of a bunch of terms. So we say this as the sum of a sub k from k equals 1 to k equals n. Meaning, I'm going to zoom in for this, meaning this is the explicit formula, and we're adding up the terms. We start with k equals 1, and we go all the way up to whatever number this is, n. So let's write something like start and finish, like that, and add these terms. So that might be helpful. Okay, here's an example. So we could say this is the sum of k squared from k equals 1 to 5, meaning what we're doing is we're taking the integers 1, 2, 3, 4, and 5, and we're squaring them and adding them together. So we plug in a 1, squared, plug in a 2, squared, plug in a 3, squared, plug in a 4, squared, plug in a 5, squared. Wish I could talk faster. Okay, and I think we get 55 for that. Next example we have, so this would be described as the sum of 1 over j from j equals 3 to 5. So we're taking 3 and plugging it in for j, and we're adding 4 plugged in for j, and adding 5 plugged in for j. And then whatever that equals, let's see, oh, I do have an answer. All right, we would do common denominator and get something like that. And lastly, this one looks complicated, but is actually the simplest of those. So the sum of I from I equals 5 to 10. So notice how there's nothing, it's not being squared, it's not being multiplied by something or divided by something. So when we plug in 5, it's just 5. And then when we plug in 6, it's just 6, and so on. So we would be adding the numbers from 5 all the way up to 10, and we would get 45, I think. Okay, so these are pretty fun when you're given the sigma notation and you write them out. It's kind of more fun when you're given the sequence or all the numbers and you figure out what the summation notation, sigma notation would be. So write the sum using sigma notation. Let's see, I think I have a Whoops, oh, I definitely have a typo down there. So we'll just zoom in and not pay attention to what I wrote. All right, so, hey, get out of there. All right, what we have is we have our integer that's being raised to the third, integer being raised to the third, integer being raised to the third. So pick a letter, any letter, we could use n. So we're going to start at n equals 1 because that's the first integer that's being plugged in. And the function is we are raising it to the third power. And we go from n equals 1 up to n equals 6. So it would look like this. And this could be described as the sum of n cubed from n equals 1 to n equals 6. And you could add all those up and get some big number. All right. I forget what that was. Okay, next up. So we know we're going to have a sum of something. We're adding stuff up. And we look at these integers and what's happening to them. Well, looks like we're taking the square root of them. We're adding them. We start at 3 and we go all the way up to 77. So pick a letter, any letter. We can use m. So from starting at m equals 3 and we're adding up m squared. And we're going from m equals 3 up to m equals 77. So we could add those up and we'd get some number. Okay. But this is the sigma or summation notation for this sequence of numbers. And then I think down here I wrote how you could change the index. So I used the variable k here, and I wrote k to the 1/2 instead of square root. So these are the same thing. But notice how we can, sometimes you want to start from an index of 1. So do you see how if we shift, so this gets reduced by 2 and this gets reduced by 2, and then we account for that here. If I were to take 1 and plug it in, I would have square root of 3, that's my first term, and then 2, and I'd have square root of 4, and by the end I'd get 75, I'd plug it in, and I would get the 75 plus 2 is 77, so square root of 77 is the last term. So this right here, I think we're going to get into this. Change of index. So sometimes that will happen. These two are the same thing, equals. All right, thanks for listening.